right, so we're continuing on with electricity, and we're going to look at something called electrical resistance, and we're going to look at the formula developed by a gentleman whose last name is Ohms. So we have Ohm's law. And so when charges, I should say, pass through a device, load, lights, appliances, they experience a resistance to their flow, resulting in a loss of electrical potential energy. And since each load, device, if you will, resists the flow of charge differently, each load has what's called a unique resistance. And so we have Ohm's law, and what I have here is an equation triangle, I like to call it. And so you can look at our formula. V would be equal to I times R down in the bottom. And if you're finding I, well, you have V divided by R. And if you're looking for R, you have V divided by I. Now, again, some of our two of our values our variables are the same as what we've looked at before with voltage. Again, voltage is how much energy each charge has. Current is how many charges we actually have going through the circuit. And of course, now the resistance is just how much, it's kind of a rating on how much loss of electric potential energy occurs when the charges go through a certain device. All right, now, looking at a couple questions here. An automobile headlight has an average resistance of 24, and see that little horseshoe there? That is a unit of ohms. It's a Greek letter. I think it's omega, but it's used in physics to denote resistance, the units for resistance, which again are ohms. All right, now car batteries provide a potential difference of 12 volts. That's actually true. What amount of current passes through the headlight? All right, so again, what we're looking at is, what do we know here? Well, an automobile headlight has an average resistance of 24 ohms. So that is our R value, our resistance, 24. I don't have a horseshoe on my keyboard here, so I'm going to leave that one. The potential difference, again, 12 volts. That is our voltage, so V equals 12. And what amount of current passes through? So we are looking for our I value. All right, so if I look at my formula triangle there, I'm looking for I, and so I is going to equal V divided by R. And so when I substitute my information in, everything's in its standard units. We have 12 as our voltage. Our resistance is 24. And so, well, 12 divided by 24, need a calculator for that one. It's 0.5, and we're talking about current, which is in amps. Probably the easiest formula we'll use, or that we have used all Quadmaster. All right, let's try, I'm going to skip one here, and we'll try another one here. What is the resistance of a 1,100 watt hair dryer plugged into a 120 volt outlet, which we all have in our house, with a 10 amp current flowing through it? It's a lot of current. All right, so here we go. The information we have, 1,000 watt, that is watts, that's power. So that's our P value, 1,100 watts. All right, our outlet is 120 volts, so that is our voltage. It's 120 volts. All right, current, we have 10 amps. All right, and what do we want to know? What is the resistance? So that is our R value. All right, so again, looking at my triangle for resistance, or the equation triangle, I have my R is equal to V over I. And what you'll see here is, yeah, I don't need power. I have it, but I don't need it. And so I always call that a cement of a question, because it's just in there to make it hard and confuse you. But it's not a value we need. All right, so we have R is equal to, we have our 120 volts. So there's our V. Our current is 10. And this is another easy math one. 120 divided by 10, well, that is going to be 12. And again, the units for resistant are ohms, which is that funny looking horseshoe there type thing. All right, now we're going to move towards circuits because we've been dealing with circuits. And there is different resistance within a circuit because we're going to piece it all together. Our circuits, and we're going to add in resistance. The other day we just did voltage and current, but now we're going to have all three variables in it. And so the resistance within a circuit works a little bit differently depending on what circuit you're dealing with. So to start off, a series circuit, the easiest one, and again, that's where the charges, as they go through the circuit, they go through each load. They don't have a choice. And so for the resistance, you just simply add them all up, no matter. So how many loads you have in series, you just simply add them up. So in this case, for this example, I have R1, R2, R3. So there is three loads. And so RO, or R naught, I should say, is the resistance of the entire circuit. All right. The 1, 2, 3, that doesn't matter how you order them. But in this case, again, you just add them up. All right. Now, parallel circuit works a little bit different. The parallel circuit, again, is when the charges leave and they actually have a choice. So in this case, they can go down load number 1, 2, or 3. They can't go down all three. They can't even go down two of them. Only three of them. And the resistance for this circuit is 1 over R1 plus 1 over R2 plus, well, you just keep adding the reciprocals up, and then you take the inverse, this -1, to the power of -1. So it's the inverse. You flip it. So again, we're going to look in this case. So in this case, again, there's three of them. So we have R1, R2, R3, and so we have 1 over R1 plus 1 over R2 plus 1 over R3. We would add those up, whatever number we get. Always going to be a decimal generally. And then we take it to the power of -1. All right, so I'm going to explain kind of how this works, these formulas too, as we go along and try some examples out. Because again, we are going to try out some circuits here. So let's see here. There we go. All right, so example 4. In the following diagrams, find the circuit's equivalent resistance. What does that mean? That means we are finding R naught. All right, so we want to find the resistance of this circuit, the entire circuit. Well, this circuit, again, is the easy one. And I say that because, well, we just have a series circuit and we have three of them in there. And just like that formula we just went through, or one of the formulas we just went through, our R naught, well, it's just simply, we add them up. So we got 2 plus 4 plus 5. And well, if we add those up, well, we just get 11 ohms. Ohms. There we go. So again, that's the easiest case. Now, the next case, again, when we get to a parallel circuit, all right? And so again, what we're looking for here is our R naught. All right, the resistance of the total circuit. So I'm going to call this one here, this is R1 here, R2, R3, and we have R4. We have 4 circuits here in parallel. Now, because it's in parallel, what we're going to do here is we got R naught is equal to, big brackets here. I got R1 here, so I'm going to have 1 over R1, or 1 over 8. Plus, R2 is 5, so I'm going to have 1 over 5. Plus 1 over 10. And then our fourth load, which has also 5, so we have 1 over 5. Now, after I add all these up, again, the last thing I'm going to do is do the inverse. So, equals. Well, again, just get my calculator out here. And so I have, let me see here, 1 divided by 8, and going to 2 decimal places, I got 0.13. Plus 1 divided by 5 is 0.2. 1 divided by 10, I know that one's 0.1. All right, plus 1 over 5 again, so that's 0.2. And again, I got to take that to the power of -1. All right, so I add all those up. And let's see here, 0.2 plus 0.1 is 0.3, 0.5, add this. I'm going to get 0.63 here. to the negative 1. All right, and then I take it to the power of negative 1. Now, if that's confusing to you, essentially what this means is you take 1 and you flip it and divide it by 0.63. That's what I'm doing. But I'm just going to put in 0.63 to the power of negative 1, and I get 1.59 ohms for resistance. Now, I want to compare something here. Is that, see, in this circuit here, our resistance is 2, 4, and 5. And our total resistance for the circuit, the equivalent resistance, is 11. See how it's higher? And in the other one, it's lower. And here's the reason. It's kind of like, well, resistance. It's like water flowing through a dam of some sort. And say there's 3 dams here, or three paths. It's got 3 obstacles here, right? You got 1 obstacle, 2 obstacles, 3 obstacles. So because the charges have to go through 3 obstacles, there's a lot of resistance. But if you look at our parallel diagram, our parallel circuit, the charges get to choose their path. And there's several paths. So it actually makes the flow of electricity easier for the charges. And so that's why you have less resistance. So something a little different. Now, of course, what can happen is mixed circuits. That's the reality of life, is that we don't get these nice, pretty resistors that are completely in circuit or in parallel or completely in series. Usually the perfect ones you're going to see are in, that's Christmas lights. So in this case, again, we're going to be looking for the equivalent resistance. All right, so where's our source? Right here. So this is the RO that we're finding. Now I'm going to call this resistor 1, this one 2, 3, 4, and so we got 5 of them. Now, it is in series, except for we got this parallel piece inside the series. So here's what I'm going to do. I'm going to find out, I'm going to treat our 2 here that I'm putting in red. I'm going to figure out what their equivalent would be if we just looked at them as 1 resistor. And so that is going to be called resistance. Let's see, we're dealing with 2 and 3, so resistance 2, 3. Now, because they are in parallel, I'm going to use my parallel formula. So I got 1 over 5. What's the other one here? 4. Okay, so plus 1 over 4 to the power of negative 1. All right, so again, looking at what I got here. So I got resistance of 2, 3. So it's acting, what I'm looking at is pretending they're almost 1 load. Well, I am doing that. What the equivalent would be if they were just 1 load. And so when I have 1 divided by 5, we already had that, 0.2. 1/4 is plus 0.25. And again, I got to take that to the power of 1. Negative 1, sorry. Negative 1. All right, so now resistor 2, 3 is equal to, well, 0.2 plus 0.25, that's 0.45 to the power of negative 1. And let's see, I end up with 2.22 ohms. All right, now, that's not what we're looking for here. We're looking for R0, the circuit equivalency. Now, because I've treated these 2 devices, R2 and R3, as 1 device, well, now I can just treat this as a series circuit. Where I'm looking at is RO, or R0, I should say again. We're going to add up R1 plus, well, I'm going to add up my R2, 3. Again, they're in series here, plus my R4, plus my R5. All right, so then that means R0 equals, let's see, 10, number 1 is 10, plus the one we just, equivalency, the R2, 3 is 2.22, plus number 4 there, which is 3. That's the reason I also label them, and 2. All right, and so the resistance within the circuit, 10, let's see, 3 and 2 is 5, 10 is 15, so it's going to be 17.22 ohms. Since I can't write the symbol, I'll write the name. And there we go. So there's an example of a mixed circuit where we have a parallel inside a series circuit. They can come in all different shapes and sizes, these mixed circuits. All right, let's see, I'm gonna do, well, I got another one here. All right, so here we go. We have our circuits. So now, wow, we got a series inside a parallel that's inside a series. That's a lot, right? All right, so again, I'm gonna label these things. Again, this is at our source. There's our battery here, so that's R naught. I'll call this 1 here, and 2 here. This guy's 3, and I'll say this one's 4. All right, so again, I'm going to use that trick where I use equivalents. So when I have R1 and R2 here, they're in series. So I can simply just put them together and say that I have resistance 1, 2 here, treating them again as just one load. And because they're in series, I just add 2 plus 3. It's 5. So there's my R1, 2, it's 5. So it's now looking like I have these two of them now in parallel. So here's what I'm going to do. Because they're in parallel, I'm going to put all 3 of these together. And here's how it's going to work. Is that when I find what I'm going to call now, because I'm putting all 3 of them together, I'm going to call it R1, 2, 3 equals, now they're in parallel. So I'm going to have my R1, 2 here is 5. So because they're in parallel, 1 over 5. Then I have my R3 here, which is 10, so I have a 1 over 10. And again, it's got to be to the power of -1. So now I've got R1, 2, 3. So this is like I'm combining all, well, it is, I'm combining all of them. 1 divided by 5, 0.2. I've had that a couple times. 1 divided by 10, that's 0.1. And again, to the power of -1. And so 0.2 plus 0.1, well, I know that's 0.3 to the power of -1. And let's see here, I end up with, when I do that, 3.33. All right, ohms. Again, there's that little funny horseshoe. So if I put all these 3 loads, 1, 2, and 3 together, equivalently, they would look like they would have the effect of having 3.33 ohms of resistance within the circuit. But again, I want to find R naught here. And so what I'm going to do, because I got this little R4 here, so if I want R naught, oh, it is in R4, they're all in series now. And so what I'm going to do is I'm going to take R1, 2, 3, and I'm going to add it to R4. And so what I get is my 3.33 ohms plus R4 down there, all lonely, is 8. And so when I put them together, let's see, well, it should be 11.33, again, ohms. And there we go. So we have to treat our circuits, we got to make equivalency. All right, so this is very important because in our next and last lesson, we are going to look at electrical circuits like we did before. Again, it's kind of like a giant puzzle where we are going to not only, again, like I was mentioning, deal with voltage and current, but we're now going to throw in resistance. 3 variables, just makes it a little bit harder. It's an extra piece to the puzzle. All right, so that is it for this section.